Food and farming are an integral part of a functioning society. Our project seeks to accelerate the growth of biomass by targeting specific wavelengths of light that plants absorb with chloroplast during the process of photosynthesis. The way we accomplished this goal was by using horticulture LEDs from Worth Electronics. These require a high-powered LED driver board. We also incorporated an automatic watering system and a soil/temperature monitoring sensors. All manual control and soil/temperature monitoring data is available online.
To successfully cultivate any plant is a formidable task. Any plant you try to grow requires careful consideration of its environmental context. Where do we stand with regards to the season? Can I expand my garden? If I fail to water the plants, what happens? How much water should I give them? What will happen to the plants if there is a drought or if I have to depart for several days? If I don't have a garden or any knowledge of plants, I have little chance of successfully growing anything. Anyone attempting to nurture plants without adequate resources is likely to run into these issues. The purpose of this enclosure was to facilitate the successful indoor cultivation of plants. Growing plants with automatic lighting and watering would cost up to $1,000. We also wanted a way to remotely manage things like watering and lighting for the plant using a mobile app. Constant availability is possible due to the system's ability to run on electricity. The enclosure could hold 50 pounds of weight and accommodate plants as tall as 3 feet. Leaving the plants for a long time without worrying about their well-being was a breeze because the user could adjust the lighting and watering from our app. Because of the system's flexibility, the user wouldn't need to hire someone to water the plants or worry about the location's lack of sunlight. If you aren't a plant expert, you might tell whether your plants were dry by keeping an eye on the soil moisture levels. Even if the user forgets to monitor the soil moisture, they may still program the system to water at a certain level without their presence being required. With a maximum height of 3 feet and a weight of up to 50 pounds, the user may choose from a wide range of plants.
The irrigation system's water is stored at the facility's basement level. The 4 and 5 volt pumps that supply the irrigation system above the plants are kept in the 5-gallon tube. We tried using smaller pumps, but they lacked the vertical water displacement power to supply enough pressure to water the plants, so we thought about switching to a gravity feed system. However, this presented a number of safety concerns that we were unable to address, given the number of electronic components used in our setup. As a result, we supplemented the basic architecture with more powerful pumps. To get the water from the tubing into the PVC, we utilized a ProLine adapter. Each section of PVC pipe has tiny holes cut into it to let just enough water through to saturate the soil. Affixed to the top of the dirt enclosure's beams of support are 4 PVC pipes. We found this to be the most economical method of watering our plants. Although burying the pipes in the ground would provide the plants with the most consistent water supply, doing so would necessitate an increase in the number of sensors and a better quality pump. Some of the LED light is blocked by the overhead irrigation, reducing its effectiveness. Following careful examination of the benefits and drawbacks, it became clear that overhead irrigation would be the best option. The pumps are activated sequentially for 30 seconds each once per day.
The control board has headers for the Pico to connect to. There are also headers for the Adafruit Airlift. We switched to the Pico W instead of the Pico with Airlift combo. There's also a barrel jack for 5 volt power. There's also a spot to add a 3.3 volt regulator and a jumper to disable the 3.3 volt buck boost on the Pico. There's also a run button to restart the Pico. On the right side of the board there are 4 pump drivers with voltage dividers on the MOSFET gate, extra MOSFET protection diode, and flywheel diode. On the left side of the board there are 4 JST headers for the 4 soil moisture sensors. On the bottom of the board there are 5 high-power LED drivers and pads for the 36-volt 1200-watt power supply. The Pico W controls all of these while connecting to ResMediaNet to push data to and pull data from the cloud. Watering is automated and happens daily.
The system lighting consists of 4 LED boards, each made with an aluminum substrate with 1 ounce copper on the substrate, 1 mm traces, and 3 mm by 3 mm HALS pads. The pad pairs are placed 7.5 mm center to center and 20 mm from center of the pad pair to the next. Each LED board has 8 LEDs, one blue 450 LED, two white broad spectrum LEDs, two far red 730 nanometer LEDs, and three hyper red 660 nanometer LEDs. The lights are controlled by 5 high-power LED driver ICs integrated into a PCB based on the recommended PCB layout. The lights can be controlled either with a resistor or a PWM pulse. We are controlling them with a PWM pulse and using a jumper to set the current to 350 milliamps. The PWM values are pulled from the cloud and set periodically. For the final design, we decide to enclose the soil and plants in a polycarbonate box that is held up by a wooden frame attached to the structure on all sides. The black caulk is used to double seal the polycarbonate planes to prevent any moisture from getting and rotting in the wood. The plants are irrigated from above using a PVC pipe irrigation system, and their soil moisture is tracked by a sensor placed in each of the 4 sections. The polycarbonate container is supported by a hardwood base that is attached to the framework and fortified at the corners with the help of a triangular bracing. This prevented the platform from bending or collapsing while the dirt was being stored. To ensure that the soil moisture sensors were providing accurate readings and that the irrigation system was distributing water evenly on the level, we divided the area of the soil into 4 sections. The soil moisture sensors are all on the same I2C bus. Each of them have a unique address ranging from 0 by 36 to 0 by 39. The soil moisture sensors are pulled every 5 minutes, and the moisture and temperature readings are sent to the cloud.
One of the strongest aspects of our design is the wooden frame. We wanted to make sure that the shell would be strong enough to hold more weight than we actually needed. If the weight of the wet soil had caused our structure to collapse, it would have likely killed the plants and ruined the electronics. We also added extra support to the sides of the enclosure to ensure no bowing occurred in the polycarbonate. Another strong aspect of our plant enclosure was our 36-volt power supply. It was able to provide 1600 watts, and our project only used around 200 watts. One of the weaker aspects of our design was the plumbing system. While the system worked without air, the PVC pipes running atop the plants were not secured and could easily be bumped out of place. The holes that we drilled into the pipes were effective, however, they did not always water in the optimal location for our plants. Another issue that we would address if this product were to come to market is the way our wires were run. It is typical that there is no exposed wire in electronic items that we buy. In our plant enclosure, we wrapped our wires around one of our back support columns to get power from our control board to the LEDs. Our enclosure is limited in a few ways. First, the enclosure would not be able to run unattended for much longer than a couple of months due to the water carrying capacity. Our water was stored at the bottom of our enclosure and could hold around 5 gallons of water at one time. Once that water had run out, it would have to be manually refilled. The water posed another limit due to it being below the plants. If the water were to be stored above the plants, a gravity-powered watering system could have been designed, negating our need for pumps. This, however, would make our project much more of a safety concern due to it being top-heavy.
Due to our decided 2x2 planting area, we were limited to the number of plants that we could grow at one time. Also, due to the time constraint of 1 semester minus planting time, we were unable to grow full plants that could have been eaten. It would have been very satisfying if we could have samples of lettuce and spinach that people could taste during presentation. In hindsight, though, it would have been better plant growth if the LEDs were closer to the plants. However, after construction and installation, it would have been a big undertaking to lower the LEDs. We also struggled with communication between the Clemson's ResMediaNet Wi-Fi and our Pico W. Almost daily, connections would be interrupted, causing gaps in our soil moisture data being uploaded to our website. It would have benefited us greatly to purchase our own Wi-Fi network, allowing our data to be much more consistent and visits to the lab less frequent.